Hello, everyone. My name is Tavares. I work at Qualcomm. I would like to take a moment to express my gratitude for the collaborative efforts that have made this project possible. The partnership between SI2 and Qualcomm has been instrumental in driving UPM adoption. Acknowledging the contributions of both teams highlights the collective efforts and dedication involved. The Qualcomm team, including myself, Joan Pratish, has played a crucial role alongside with SI2 members Leanne, Ali, and Jerry. The support and regular status meetings have ensured that we've stayed on track and aligned with our goals. So let's start with Qualcomm's technologies motivation for UPM. We're driven to bring about standardization of models and tools used at system level. Currently, power analysis at the system level is done using company-specific models, formats, and tools, which can be inefficient. The benefit of UPM to Qualcomm are significant. For one, it provides single, scalable models that can be used across various design levels, from circuits IP to hard macros to subsystems to SoC. This model can be applied to all stages of the production development, from architecture to RTL to implementation stages, and it works across different PBT corners. Another key advantage is that UPM is a non-proprietary format, which reduces complexity for scaling setups and enable easier collaborations and data exchange. This in turn leads to improved efficiency, reduced library characterization turnaround time, and faster enablement of new PBT corners. In terms of accuracy, UPM delivers SPICE accurate results, similar to Liberty, and allows for late binding PBT power analysis, which provides more accurate power estimation. Overall, UPM provides a powerful solution for power analysis at the system level, and we're excited about its potential benefits for our business. This slide highlights the key features of UPM, emphasizing its unique power analysis capability. The late binding PVT power analysis allows for flexibility in handling various process, voltage, and temperature conditions. The multiple data representation, including scalar tables and expressions, provide a comprehensive view of power metrics. A bottom-up approach is utilized to dissect power contributors at the cell level, which is crucial for identifying inefficiencies. Additionally, the slide mentions the separation of leakage and dynamic power representation, with leakage power being calculated through expressions and tables. UPM adheres to the IEEE 2416 standard, ensuring interoperability with UPF and IEEE 1801, and is built on XML, which enhances its integration capabilities across different platforms. This slide emphasizes the importance of using models in the context of power management and architectural exploration. It highlights how power KPIs can be projected dynamically based on frequency and bandwidth, which is crucial for optimizing performance. The estimations of days of use is also discussed, indicating that ongoing projects should refine their days of use estimates as use cases evolve. This iterative approach enhances accuracy over time. Additionally, the concept of seamless model generation is introduced, underscoring the role of standardization in ensuring continuity and fostering ecosystems development. By integrating directly with EDA tools, this process supports both upstream and downstream workflows, enhancing overall efficiency. The UPM validation plans outline a comprehensive strategy for Qualcomm Technologies and SI2 to develop system-level power representation using IEEE 2416. The primary goal is to ensure that all use cases of two subsystems are accurately represented, allowing for a thorough understanding of power dynamics. This involves demonstrating that all relevant parameters can be manipulated through various available methods, such as expressions and user-defined parameters. Additionally, a utility will be developed to aggregate power data across subsystems, enhancing visibility into system-level power consumption. The secondary goal is to include validating the power model's scalability across different operation conditions. With a structured three-phase validation approach, encompassing cell level, IP block level, and system level assessments. The accompany table outlines the specific task and dependencies, highlighting collaborations with the design team and the development of a utility for computing roll-up power, ensuring a robust validation process. We will now go over cell level validation. This slide focuses on cell level validation, specifically using a linear feedback shift register, LFSR, as a test vehicle. It is important to highlight that each cell within the LFSR was subjected to exhaustive testing, ensuring that every possible scenario was evaluated. The results from this testing were then compared to the Liberty models, which serve as the benchmark for accuracy and reliability. This comparison is crucial as it validates the performance and correctness of the LFSR implementation. Emphasizing the thoroughness of the testing process will help underscore the robustness of the validation efforts undertaken. This slide focuses on cell level setup for establishing accuracy in 6 primitive cells used in the LFSR. The goal is to ensure that these cells perform reliably under various logical and electrical conditions. The contributors have characterized a comprehensive 10x9 voltage and a temperature matrix, which specify voltage range from 0.505 volts to 0.99 volts, and temperature ranging from 0 degrees Celsius to 125 degrees Celsius. Additionally, leakage currents have been calculated for all possible states across different corners, which is crucial for understanding performance under varying conditions. The accompanying table outlines the number of modes for each cell type, highlighting the complexity and versatility of the design. This detailed characterization is essential for optimizing performance and reliability in practical applications. This slide presents the results of UPM PowerCalc static power compared to Liberty data, focusing on the percentage difference statistics for all cells. NAN4 and DFFR are the results of the two most challenging cells. The table highlights key metrics such as minimum, maximum, average, and standard deviation of the differences observed. Notably, the minimum difference is negative 0.185, indicating that there are some instances where the UPM PowerCalc results were lower than Liberty, while the maximum difference of 0.507 shows cases where the results were higher. The average difference of 0.049 suggests that the results are relatively close, with the standard deviation of 0.068 indicating some variability. This analysis is crucial for understanding the accuracy and reliability of the UPM PowerCalc results in comparison to established Liberty data. We will now go over IP block validation. This slide focuses on block level validation, specifically using the test vehicle named test block, which is an asynchronous FIFO. This design is larger, allowing for more comprehensive evaluations of the end-to-end flow. It is important to note that there are 1,371 instances in this design, and correlation checks have been performed for each individual instance. This thorough approach ensures that we can identify any potential issues early in the process, leading to a more robust and reliable system overall. As we move forward, we should consider how these validations can impact our overall design strategy and performance metrics. This slide focuses on the process of validating the accuracy of the LFSR block. With 1371 instances of standard cell, it highlights the complexity of the design, which utilizes two separate libraries. The functional simulation aspect is crucial, as it allows us to test various rewrite modes on the FIFO, ensuring accuracy of the power calculation. To ensure reliability, we use PowerCalc to compare the results against Liberty leakage data. Comparing netlist results against a commercial power analyzer is a key step in verifying performance metrics. The accompanying diagram visually represents the netlist, providing a clear understanding of the design, architecture, and functionality. With UPM library contributors can be evaluated at any VT within characterized range, not just the characterized points. The slide represents the results of the IP block analysis for the test macro netlist, focusing on the comparison between UPM PowerCalc and a commercial power analysis tool. The scatter plot illustrates the correlation between the two tools, highlighting UPM accuracy and power calculations. The accompanying table provides detailed statistics on the percentage difference across all instances, showing that the variations of the total netlist power are minimal, with the average difference of just negative 0.0006%. Such close alignments between the two tools suggest the UPM PowerCalc is a viable option for power analysis, offering confidence in accuracy. This data is crucial for stakeholders looking to optimize power efficiency in their designs. This slide delves into the generation of abstract power models for IP blocks using UPM framework. It highlights the flexibility of UPM in supporting both gate-level and abstract models, which can be utilized interchangeably for system-level modeling. A key feature is the automatic creation of abstract blocks, streamlining the modeling process. The UPM standard plays a crucial role in compressing complex models, which is essential for efficient analysis. Notably, the abstract process discards netlist interconnectivity and aids with compression of the block. The entire process is efficient, taking only 7 minutes to generate the abstract model, making it a valuable tool for rapid development and power modeling. This slide represents the results of a comprehensive leakage characterization run utilizing a single voltage temperature independent model. The analysis spans 13 different temperatures and 11 different voltages, showcasing the versatility of the UPM PowerCalc tool, which simplifies the generation of these data points. Each evaluation was efficient, taking only 4 seconds per data point, allowing for rapid results. The accompanying graph illustrates the relationship between leakage, power, and temperature across various voltage levels, providing valuable insights into the performance under different conditions. This data is crucial for understanding power consumption and optimizing device performances.